Okay, this is the system that we're dealing with here. This point over here is the center of mass of the whole system. From radius RA from that is the star MA, and from radius RB from that is the planet RB, and that's on the other side uh, of the star. So, other side of the orbit is the star. And so in part A, we use the definition of center of mass coordinate. So that's m sub I, sum of all the masses times the center of mass coordinates over the total mass. So in this case, it will be ma times ra plus mb times minus rb, opposite side, over ma plus ra. And we set our center of mass to be at the 0 point, so that's 0. Therefore, ra will be equal to mb over ma times rb. In part B, we figure out what RA is. RA is 1 times 10 to the negative 3 MA over MA times 8 times 10 to the 11 meters for RB. So the MAs cancel, and you get 8 times 10 to the 8 meters. All right, in part C, our situation is something like this. 2RA, twice the radius or the diameter of the star's orbit, is what we can see. The distance d is the distance to it, and theta is the angle that that it subtends in the sky. And so tan theta is 2RA over d. Therefore, and so since we know that this angle is really, really small, it's a fraction of an arcsecond, which is a small fraction of a degree, which is a small fraction, which is a fraction of a radian. Anyway, you get the point. Theta is small; it's tiny. So for small theta, us astronomers use what I like to call what we call the small angle approximation. Theta is approximately tan theta. That's the approximation. So in this, so 2RA over d is approximately theta. Therefore, d will be 2RA over theta. Now, theta is a whole beast in itself. It's 1 milliarcsec, so 1/1000th of an arcsecond, arcsec, times, which is an arcsecond is 1/3600th of a degree. So 3600 arcseconds in 1 degree. That cancels out the arcseconds, but we want it in terms of radians. So remember, 180 degrees has pi radians in it. Okay? All right, so this gives us This gives us 4.848 times 10 to the negative 9 radians. That's theta. All right, and so this means that d is equal to 2 times 8 times 10 to the 8 meters over 4.848 times 10 to the negative 9 radians. And so that's the unit we want it in. And so what we really have is a unit of meters in meters. And so this is 3.3 times 10 to the 17 meters. But we want it in terms of light years. So 1 light year is 9.46 times 10 to the 5 meters, or 10 to the 15 meters, excuse me. So this gives us 35 light years for the distance to the star. Okay, and part D finally is probably the most interesting part of the problem. You want to figure out how many of these stars we're going to detect, assuming a uniform distribution of stars in the galaxy we live in, which is the Milky Way. How many of these stars how many of these wobbles, how many of these stars can we detect in this method, by this method. So the number of stars, so we're assuming, we're going to assume spherical volumes throughout this part, right? So we're going to, what this means is that first we have volume of wobbles, so volume of stars that are detectable by this wobble method. So that's 4 pi over 3, volume of a sphere is 4 pi over 3 times r cubed. R is the distance to it, so that's 35 light years cubed. And then we have the volume of a star itself, which we will assume to be 4, again, 4 pi over 3 times 1/2 the distance to the nearest star, which is 2 light years cubed. Therefore, the number of stars is equal to volume detectable from the wobble method, or right, over the volume of the nearest of a single star. So that's 4 pi over 3 times 35 light years cubed, over 4 pi over 3 times 2 light years cubed. And so this gives us about 5,400 stars. And that's it.